Very good afternoon to all. Today I am talking about basically semiconductor physics is in Fermi functions, different Fermi functions in terms of material. Basically, the Fermi energy changes in terms of degeneracy and non-degeneracy Fermi in terms of material constant. Basically, in case of degenerate. In case of degenerate semiconductor, basically the Fermi functions not as a conventional Fermi functions F0 with Fermi functions some changes in terms of heavily doped semiconductor is forming a bundle. We discuss this part. Also, we investigate about the Fermi distribution function in terms of carrier degeneracy. There are various type of transport coefficients, electronic devices, and we calculate about in a gallium arsenide examples like this. In case of Fermi distribution functions, basically if the effective Fermi functions is del F, we consider the Fs minus F0, basically the degenerate Fermi functions and conventional Fermi functions difference with respect to Fermi functions, conventional Fermi functions. There are some variety about the increases with energy variations and higher value of energy. So degenerate Fermi functions is approaches to F0 like here. Another is the Boltzmann transport coefficients. In terms of degenerate semiconductors is we can change something, and also we our new experimental value about the Fermi energy in terms of degenerate semiconductor. They are near about F0 in terms of literatures like this, same like in experimental value also. And also we analysis about the Fermi distribution functions in case of carrier degeneracy with a transport coefficient, and the electron dynamics of degenerate semiconductor based on the electronic devices like this. So basically, we discuss about this part. This figure is very vital about the two Fermi functions F0 and Fs. F0 basically the conventional Fermi functions, and Fs is the degenerate Fermi functions. Both are step-like natures, and when starting from 0 to 1, so low level to high level. But F0 Fs is the more effective than F0. Basically, the degenerate Fermi functions is more effective F0 with higher concentration values. Another, the relative Fermi functions del F by F0 is the del F is the degenerate Fermi functions when difference with the conventional Fermi functions by Fermi conventional Fermi functions. Initially it is 0, then it is decreases with the reach the value minimum value in that point, and then it is increased slowly with energy increase, and on a higher value it is Fp basically approaches to F0 in conventional energy. So theoretical equation in terms of theory, basically the conventional Fermi functions like this energy E minus EF is the energy, and ENS is the basically the energy conduction band edge. They are band indexing N and S index and spin index systems. So the concentrations like this is in for degenerate semiconductor. If we in case of degeneracy, increase the skinning potential. If increase the skinning potential, so impurity potential increase means in skinning potential also increase this part. So the potential functions like here, this potential is depending with the impurity skinning potential. This impurity skinning potential is very vital. Eta is not equal to 0. If eta not equal to 0, this means it must be parabolic band, semiconductor band. So it is non-parabolic one in terms of non-parabolic one, and energy like this is E minus EV. This functions is energy is in the gamma. So gamma in terms of energy in skinning potential function. This potential function is dependent with the error functions dependent, and it is eta not equal to 0 for this case, or energy less than 0. So the function's energy in skinning potential, it basically +1. If it is a +1, so energy band is the tail into forbidden region and form a band tail like this. Okay, now in this case the average energy for like this average energy in terms of gamma for band tailing formations when E must be less than 0. So this case, the skinning potential E, basically E by epsilon D, basically in terms of in a concentration dependent, in concentration increases, in skinning potential increases also. So in this case, the functions Ni for concentrations is also Kd dependent. Kd is the must be error functions, and eta is 0. The formation is like a parabolic 1. So this energy in case of degenerate semiconductors, the Fermi functions like this. So average energy, Fermi energy is like here, and this energy is in case of non-degenerate Fermi functions, and this non-degenerate Fermi functions basically if eta is equal to 0, so this energy, average energy is equal to the energy, and Fermi energy is average also the EF. If this condition is arising, so the EF is equal to it must be degenerate Fermi functions like this. So basically, Fs is approaches to F0. These conditions, it must be equal as usual conventional Fermi functions. Okay, so now this is our value about like this effective mass epsilon D and temperature. Like the two functions F0 and Fs, both are in a step-like natures. From 0 to 1, the Fermi functions, and we apply the gallium arsenide is a semiconductor materials. So where Fs and F0, for this case conditions, Fs is more effective than F0 because the concentration is very high in this case. And if concentration high means the impurity, basically the impurity potential is high. If impurity potential is high means in case of degenerate semiconductor, the skinning is increases, skinning potential increases, so means it must be more effective for Fs than F0. So in this case, the gallium arsenide for the effective relative Fermi functions, basically the delay by F0 is delay by F0. Basically, it must be decay at from 0 to this higher energy. If its energy is increased, means the energy increase it must be positive value for these average conditions, the Gaussian representation of this case. So the energy is minimum for these conditions, then it is reach higher for higher energy, and it is reach the FA Fermi degenerate Fermi functions is equal to the Fermi energy. Fermi functions in case of conventional Fermi functions or gallium arsenide at temperature 160 to 180 like this Kelvin temperatures. So this property basically we discuss basically our the EK dispersion relations. The EK dispersion relation is newly formulated from these conditions, and also investigate about the various type of transport coefficients, the such type of low dimensional materials, and also the degenerate semiconductor, their forbidden energy gap must be forbidden gap is the band tailing is occurs for heavily doped semiconductors, but this observation is never possible in case of conventional scenario for Fermi functions, simple energy E and EF and temperature relations. This is our reference. My research collaborator and my students. Thanks.
Open for questions.